Hey, hello and welcome back everyone. Moving on to chapter 2 in the book, we're finally going to actually formally encounter what differential calculus looks like in a multivariable context. So we'll reanalyze partial derivatives today, but really there's more important, more conceptually notable material than just that of the partial derivative today. So I want to start with this preamble that I have in the chapter, which is really to address the fact that we entered the world of multidimensional functions and domains and even the fundamental theorem of calculus just a little bit right away, and then quickly changed perspectives over to linear algebra. And it may be confusing why we did that, but ideally this preamble can kind of join the two together for us, and we can see why linear algebra would have been so important before we really get into multivariable differential calculus. Let's just start out with the equations of lines again. Remember, this motivated linear algebra for us as well. Really, linear algebra is the higher dimensional version of these. And if we think about derivatives, what was the most important part of derivatives was the idea of a tangent line. So it turns out tangent lines, right? At least we encountered them in calculus 1. Derivatives were defined, at least one way of defining them, to be the slope of the tangent line. In our case, specifically m tan, right? You would find out that m tan, if you were asking for the tangent line to the function at the point x0, f of x0, draw some plot up here. I've got a function, f of x, and maybe there's a specific value x0 at which I would like to construct a tangent line. So we have a line here at the point x0, f of x0. The question of the slope of that line was answered by the derivative of the function evaluated at the point. Well, in higher dimensions, we studied linear algebra to discover, more or less, that the higher dimensional versions of lines are these objects. And these objects look particularly ugly, right? I just want to point out M11, M12, M1n, M21, M22, M2n, M1, M2, M should be Mn here. Basically what we have here is F equals a matrix, right? This is a big matrix, M11, M12, dot, 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 M1n, M21, M22, dot, 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 M2n, dot, 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 M1, M2, dot, 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 Mn. Some giant matrix acting on the kind of a vector x plus some vector b, b1, b2, dot, 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 bm, right? So it's a matrix. The replacement for the slope in a regular function y equals mx plus b is now a matrix, capital M, where kind of each of these lowercase m's, each of the entries in the matrix describes some version of a slope, right? Entries describe slopes assigned to both inputs and outputs, and output directions, input and output directions. So in this case, we have, mx, x here is our input to y equals mx plus b. And of course, the y on the other side, this is the output. And you can think about the slope m as a relationship of the input to the output, right? It's the rise over the run, the rise being the output, the y value over the run being the input, the x value. And so each of these entries inside my matrix, they describe a version of a rise over a run, depending on how I interact with the input versus the output. So you can think about, I'll just do one example here. Let's do the 2-1 entry. This is the rise of the second output over the run of the first input. And so, if you have a multidimensional function, you have multiple rises determining the outputs, right? So you have more than one output. You also have multiple runs because you have different inputs. And so each m inside of this matrix will describe an interaction of a different rise to a different run. And it's just going to incorporate all possible combinations of those. And then our derivative, the derivative in some sort of multidimensional sense, which I'm going to call df, the derivative of a multidimensional function, this will just be defined to be that matrix. It's going to be the slopes, the rise over run of these tangent functions. But these tangent functions are a little bit broader than just tangent lines, right? Because we're no longer working in one dimension. We're now working with kind of the linear algebra version of y equals mx plus b, where now we can exist in higher dimensions. But it's just that tangent slope, right? The slope of the tangent linear algebra function is how we're going to define the derivative. So that's why we cared so much about linear algebra before entering differential calculus. If we wanted to get a better understanding of what linear functions in higher dimensions actually looked like, and then in fact their slopes being the entries of a matrix. Moving on to the section of the total derivative, often we just call it the derivative, but sometimes the total derivative. I want to start with the remark here that basically addresses the fact that we understand matrices as linear functions and we understand vectors as multidimensional points. Okay, and we're going to use that notation whenever possible because the matrix vector notation tends to make statements easier than directly referring to linear functions as, linear functions as I've shown here. So we would replace this linear function with the matrix of its coefficients, 1, -2, 2, -1, shown below. And similarly, we can think about the entire output of the function rather than a point in R2 is now as a vector in R2. So vector instead of point. Now that doesn't mean we necessarily need the output to always be interpreted as a vector. This is just notationally, it makes our lives a little bit easier. So from now on, if I can, I will refer to linear functions as matrices and points in higher dimensional space as vectors. So before we get into the full total derivative, which is this matrix that we're analyzing, kind of the tangent matrix, or the slope of the tangent line, it's the entries of the tangent matrix. Let's talk about partial derivatives again. In chapter 0, we analyzed the naive definition of the partial derivative. And if you still want to think about the naive definition in your head as how to compute it, totally fine. That is really how the partial derivative gets computed. Here we have the true definition of what the partial derivative fundamentally is. So the partial derivative in a specific direction, which we're going to call x sub I, and this single direction has to be a single entry in the domain of f, technically in the argument of f, will be denoted by partial xi, or sometimes the partial with a subscript xi, and it gets defined more or less how you would expect, but here we're actually going to use the limit definition of a derivative. So we say that the partial derivative partial xi, we're going to isolate that entry, so this xi and that xi are the same ith entry in the inputs of f. Okay, so the ith entry in the inputs, we're going to look at the ith entry and we're just going to include the limit definition of the derivative inside that ith entry. So here you're looking at f. Specifically in the ith entry, we're going to move forward by a small amount just in that entry, and then we're comparing it to not moving forward at all. And then we are going to divide by the amount moved forward. And then we finish taking the limit as that amount tends to 0, right? So this amount we move forward as well as divide by is going to tend to 0. And what this is analyzing for us, right? This is truly constructing. Well, that's the rise, right? The numerator is the rise over the run in the direction of xi, whatever this xi entry is. That corresponds to a specific direction in the input space. And so we have the rise over run in that specific direction. We're going to go ahead and take the limit of the difference quotient to get the partial derivative. Now, how do we end up with the outputs, kind of the rise? What is the output rise? Notice that these f's on the right-hand side were possibly had more than one output. So we apply this difference quotient to each output individually. So you'll see that below when I actually go through an example of me actually using the limit definition. I know it's been a while since everybody's used their limit definitions, so just bear with me while I go through the example, and we'll maybe put one exercise of a limit definition in the assignment, but just one, and probably a fairly easy one for you. So you can do it at least once, but in reality, we never use the limit definition like you never did in Calculus 1 either. But we'll go ahead and use the limit definition here. So if I'm going to take partial x of this function, whose output is x cubed y squared z, and then sine xy as the two outputs, we're going to go ahead and take the limit as epsilon tends to 0. Since my partial derivative is an x variable, I'm going to isolate the x variable in both terms. There's two of them. And I'm going to modify the x variable into x plus epsilon. right? This is me perturbing forward by an amount epsilon, and then I'm going to go ahead and subtract the x variables without adding any epsilons to them, and then I'm going to divide everything by epsilon. From this point, I'm just going to use kind of vector subtraction to combine my vectors together. So I'm looking at the first row minus the first row. There's my first row minus my first row, and then the second row minus the second row. There's my second row minus the second row. Moreover, I've taken this epsilon in the denominator. I've called it 1 over epsilon as a scalar multiplier, and then once it's 1 over epsilon, I can apply it, distribute it to each entry inside the vector, and when I distribute it to the two entries, it just looks like we have regular difference quotient derivatives in each entry individually. So I go ahead and need to compute either of those two difference quotients. Of course, the limit can also distribute into my vector. So let's analyze each of these difference quotients individually. We can analyze the top row first. So if we analyze the top row and we want to actually compute the difference quotient, or the limit of the difference quotient, it's always advantageous when we have a polynomial. We will want to expand, then simplify, and cancel epsilons. Okay, so we're going to start by expanding. I've used Pascal's triangle, or the binomial coefficients, to expand a cubic. That means that the coefficients on the expanded cubic are 1, 3, 3, 1. That's what Pascal's triangle tells us. And then the powers of each of the entries, x and epsilon in the cubic, they start at a 3, and then there's an epsilon to the 0 here, 2, and then an epsilon to the 1, 1, and epsilon squared. And then there's an x to the 0 epsilon cubed there. So if you've never seen binomial expansion, go ahead and look it up. That can save yourself a lot of time on these problems. So that's how we expand the cubic. Then we're just going to go ahead and simplify that numerator. So we're going to kind of distribute this y squared z to every term inside of the cubic. There's going to be 4 terms there. And it turns out exactly one of the terms, in fact, the leading term, x cubed y squared z, that's the term that exactly cancels with the remaining term, x cubed y squared z. Okay, so those terms have canceled. What are we left with? We're left with 3x squared epsilon y squared, 3x squared epsilon squared y squared z, and epsilon cubed y squared z. At this point, you can go ahead and cancel the epsilon in the denominator, right? Because if I distribute the denominator epsilon to all 3 terms in the numerator, I'm going to go ahead and distribute, cancel. The 2 becomes a 1, the 3 becomes a 2, and we end up with 3x squared y squared z plus 3x epsilon y squared z and epsilon squared y squared z. Once the epsilon disappears from the denominator, it's really that division by 0, right? The fact that you would send the epsilon to 0, dividing by 0 is what would normally screw up taking the difference quotient. So once you've canceled that, you can go ahead and allow epsilon to go to 0. There's going to be one of them right here and one of them right there. That makes both of these terms fall out, and you're just left with 3x squared y squared typo z. So 3x squared y squared z is what you would get using the limit definition of the partial derivative in x. Not really a surprise, right? If you use your naive definition there and consider y squared and z constants, what's the power rule on x cubed? You get 3x squared. So you exactly get the same answer you would expect using the limit definition. And then if we analyze the second entry in the vector we had, which was this case of the sign, we have sine of x plus epsilon y minus sine xy all over epsilon. We're going to have to go ahead and simplify this. First thing that needs to happen, we can distribute y to both the terms. We get an xy and an epsilon y. Now it gets tricky. How do we simplify something like this? Well, we're going to use the sum of angles formula for sine in particular. Because we have a sum of the angle xy and the angle epsilon y. Sum of angles says you take each of the angles, you get sine of the first, cosine of the second, plus cosine of the first, sine of the second. Now, how are we going to simplify this a little bit farther? Well, we recognize that, okay, there's a sine xy here, there's a negative sine xy here. Those don't quite cancel because of this cosine epsilon y getting in the way. But what I can do is I can go ahead and grab this sine and that sine, group them together, and then factor it out. So if I factor that sine out, what am I left with? I'm left with the cosine epsilon y minus 1, right? There's the minus 1, and I still have an epsilon in the denominator. So there's my epsilon in the denominator. Now that's actually useful because there's a formula. This is part of the definition of sine and cosine, actually, that the limit, as I'll just use regular epsilon here, goes to 0 of cosine epsilon minus 1 divided by epsilon. This limit is actually 0. And you could always use L'Hopital's rule to get yourself there, but that's kind of circular reasoning because you would need to know the derivative, using derivative rules to use L'Hopital's rule here. But anyway, it turns out that that term will end up going to 0 based off of the definition of cosine. And then the remaining terms, or the terms I didn't group together, was this one. We bring that over to the side here, and actually I'm going to keep all my terms with epsilon on one side and then my one term without epsilon, cosine xy on the other side. This is useful because we also have a similar identity for sine, which says that as epsilon goes to 0, the ratio sine epsilon over epsilon goes to 1. Now what that means is if I go ahead and add a y in here, a y in here, and a y in here, the answer still goes to 1, but the price I pay for putting a y in the denominator is to add a y into the numerator, so you go ahead and add a y into the numerator, and that's where we're picking up this y from. So the limit of sine epsilon y over epsilon by itself would just go to y times 1. So we end up with a y in front of cosine xy here. And so what we get out of the final answer, there's a 0 that shows up, and then y cosine xy. Which, as before, if you just use your kind of your cheating partial derivative rules there, thinking about x as the variable and y as the constant, you take a derivative, you have the derivative of sine, which is cosine, and one chain rule in the direction of x is going to give you a coefficient of y as your answer. So everything agrees. I also go through the work of computing the partial derivative with respect to y using the limit definition here as well. In case you were curious, you get exactly what you would expect, right? A derivative, remember where we started, we had x cubed y squared z, and we had sine of xy here. And so what you're going to end up getting, if you take a derivative in the direction of y, keeping x and z constant, you're going to pick up exactly a 2y, and everything else remains constant. Or in terms of sine, the sine will flip over to cosine, and you take a derivative using the chain rule in the direction of y, you're going to pick up an x out front. So everything kind of works the way you'd expect, and then I also provide the examples via shortcuts where we think about keeping every other variable as a constant. This is exactly the shortcuts we experienced in chapter 0. So if we take a partial derivative in the variable x, we're going to think about this as an ordinary derivative in the variable x, where the other variables are held constant, and you end up exactly where you want to end up. So I'm not going to recover any of those, but the examples are in the book for you, including this lovely 4-dimensional example that's a little bit more complicated. But now we're actually going to talk about the derivative. This is really what I want to cover for the day, which is this object, this matrix, which we're calling m tan for the tangent matrix. And this matrix will be defining the derivative for us. So we're taking this idea of a derivative, whatever that is, in quotes, derivative, as an idea, and we're formalizing it, the idea, to become the tangent matrix. Turns out the notion of a tangent matrix is a lot easier to define than the notion of a derivative. So let's look at kind of one of the classic examples here, the function f of xy outputting x squared plus y squared. This is known as a paraboloid, because we'll see below this looks like a parabola rotated around the vertical axis. So a very common function to refer to for 3-dimensional problems now and then. Well, really 2 input dimensions and 1 output dimension. And we can plot this in 3D, since the input is 2-dimensional and the output is 1-dimensional. So we only need 3 total dimensions to plot this. How do we plot this? Well, shown it here. We basically allow x to be the horizontal input, y to be the input that comes out toward us, and then the values, right, we're going to go up until we run into the value of f of x and y. Okay, so you do this for every single point, in the xy plane, and then you just plot the heights out, and you end up with this parabola looking structure. Okay, but given that function, what we're actually curious about is like this object, which we're trying to call the tangent. What do we want to call this for now? Tangent affine function, right? This is a function which is quote unquote flat, right? It's the equivalent of a line, so the slope is constant, and intersects at one point where the slope, let's say each slope, matches the local slope of the surface. So we want to find a function like that, or whatever this object is, and what that looks like, if I just select the point 1, 1 here, or 1, -1 here, it looks like, the following disk, but this is a disk which is a portion of a plane. Now, planes are specific to functions which map 2 dimensions into 1 dimension. These are very common functions, and of course planes are very common objects. So basically what we're constructing here is a tangent plane. You imagine if I held up a piece of paper to this cup-like parabola, how I'm basically asking a question, as long as the paper is rigid, what is the closest the paper can approximate the parabola specifically at the point 1, -1. And the question becomes, what is the function of the plane? Well, it turns out that if you just kind of look at the plane and you look maybe in the x direction here as well as in the y direction here, you can ask questions, what is this slope in the x direction of the plane? What is this slope in the y direction? It's not too hard to find out that in the x direction, the slope is exactly partial x of our function evaluated at the point we care about. What's the point we care about? It's 1, -1. And then the slope in the y direction is exactly partial y of f evaluated at the point we care about, 1, -1. And so we have these slopes of these two lines that describe the plane for us. Now, how do those slopes actually intersect or interact with the way you would represent a plane here? Turns out all planes can be represented as the following. You have the x slope and the y slope. But because that x slope and the y slope are exactly the partial derivatives in x and y, you find out that, well, really this matrix, interpret this as a matrix, that matrix is constructed precisely from partial x f and partial y of f. And so because we're defining the matrix to be the same as the derivative, you find out that the derivative of this function should be defined to be equal to the matrix whose entries are partial x f and partial y f. So this object we call either the derivative or the total derivative. But we can make the same argument in any number of input and output dimensions. What that ends up looking like is you define the derivative, at least in coordinates. These are called Cartesian coordinates. When you define the derivative in Cartesian coordinates, you define it just to be equal to, if my function has x1, x2, all the way to xn as inputs, it's partial x1 on the function. And then the next entry of the matrix is partial x2 of the function. The next entry of the matrix, eventually partial xn of the function. Now, because each f has multiple outputs, we think of each entry here as a column of the matrix. Okay, so this whole term is the first column of the matrix. This whole term is the second column. That's the very last column of the matrix. So this is called the derivative of a multidimensional function. Let's look at an example here. So here's a multidimensional function. It maps R3 to R3. We have the first output as x squared y cubed plus z to the fourth. The second output is x cosine y. The third output is the square root of 1 plus z squared. And for the time being, we're going to rename the first output as f1, the second output as f2, and the third output as f3. Makes our life easy to think about it as a matrix when I give them the names f1, f2, f3, because if I just write out the definition of the multidimensional derivative, we say it's partial x on the entire function, partial y on the entire function, and partial z on the entire function. But because we've kind of turned all of the outputs of f into f1, f2, and f3, makes it a little easier to reinterpret the derivative as a matrix, right? The derivative truly is a matrix where all of the columns are exactly the columns of the original function, and then the rows change between the partial derivatives. So you go partial derivative x, partial derivative y, partial derivative z across the rows, x, y, and z across the row, x, y, and z across the row. At this stage, we just go ahead and actually compute the partial derivatives for every single entry, and we end up computing those. What do we actually get? Well, you get the derivative in the x direction of x squared plus y cubed plus z to the fourth. That's just going to be 2x. The derivative in the y direction of x cubed, or x squared plus y cubed plus z to the fourth, it's going to be 3y squared. The derivative in the z direction of x squared plus y cubed plus z to the fourth is going to be 4z cubed. The derivative in the x direction of x cosine y is just cosine y. The derivative in the y direction of x cosine y is just negative x sine y. And then the derivative in the z direction of x cosine y, of course, is going to be 0 because neither x nor cosine y depend on z. Finally, in the last entry, partial x against square root of 1 plus z squared is going to be 0 because there's no x's there. Partial y on square root 1 plus z squared is going to be 0 because there's no y's there. And then partial z on square root 1 plus z squared will just be the ordinary derivative in the direction of z of the square root of 1 plus z squared. That ends up being z divided by square root 1 plus z squared. And then finally, I have this message here that I always want to remind you, as the interpreter here, that the output, even though it's represented as a matrix, it really should be represented as a matrix, should also be considered a multidimensional linear function, right? This matrix is representing a linear function, and that linear function is describing the slopes that interact between every input, meaning the run of the slope, with every output, being the rise of the slope. Got another example of the derivative computation. Here's a function from 2 dimensions to 2 dimensions called g. The first output is square root of x squared plus y squared plus 1. The second output is xy. Let's just think, without me going through all of everything I've got below, let's just think and compute this derivative ourselves. What are we going to do? We're going to compute partial x on g, and then partial y on g. We're just working our way through every single input and output of g for the partial x and the partial y. If g had more inputs, then we would have to add z or w and so on. But now let's think about, well, what is partial x of the vector g? Well, we're going to take partial x on the first output, which is x squared plus y squared plus 1, and then a square root. That's going to give us, if we do partial x, what's that giving us? Well, it's going to give us a 2x from taking the chain rule on x squared, but it's also going to give us a 1/2, then a square root of x squared plus y squared plus 1 in the denominator. So those 2's can actually cancel, and we're just left with x over root x squared plus y squared plus 1. Then if I look at partial x of the second entry of g, right, because this is the entire vector of g that goes here, and so you need the entire vector of g going here. If I take partial x on the second entry, that's xy, that output's just going to be y. If I take partial y of g, then in the first entry, I'm basically trading every x for every y from my earlier computation, so I'll end up with y divided by the square root of x squared plus y squared plus 1. And then the second entry of g is xy, so a y derivative there will be an x. So that's going to be the derivative of this multidimensional function g. And of course, if I scroll down, we see exactly the answer that I just came up with, describing the steps to you. Once again, even though it's a matrix, think about this as a multidimensional linear function. This is at every point, at every input, these usually go as x0 and y0. These are the points at which we would like to find a tangent function at. So if I plug in an x0, y0, this now describes the slope, quote unquote, of the tangent function. There's one more example here in the case of mapping 4 dimensions into 1 dimension. Because there's going to be 4 inputs, our derivative will have 4 partial derivatives in it, right? You need a partial derivative in every direction of the input. Well, you go ahead and compute the partial derivative in the direction of x, you're just going to get 4x cubed. The rest come along for the ride. If you do a partial derivative in the direction of y, you're going to get 3y squared, and then everything else comes along for the ride. If you do a partial derivative in the direction of z, you're going to get 2z, and everything else comes along for the ride. And partial derivative in the direction of w, the w is just going to turn into 1, and everything else comes along for the ride. And so in that case, of a 4 to 1 dimensional function, you just end up with a 1 row and 4 column matrix. All right, we're going to stop there for today because I think this next section on the directional derivatives and the gradient vector serves well in its own sense. It's kind of a new interpretation of the derivatives we've had. So we're going to stop there and we're going to make sure we fully understand the derivative of multidimensional functions and what they represent before moving ahead. See you in the next one. Bye.